Alright, question number 8 is calculate the flux of a pathway where the forward velocity is 2 millimolar per second and the reverse velocity is 1 millimolar per second. So flux J, this is actually a pretty easy question to solve. Right. When we're talking about metabolic pathways and the velocity or the velocity of those metabolic pathways, really what we're concerned about is the flux. How much of these metabolites are going forward versus how many of them are going backwards. Now, flux is simply the forward velocity minus the reverse, or sorry, I wrote that wrong. Forward velocity minus the reverse velocity. So in this case, our forward velocity is 2 millimolar per second. And our reverse one is 1 millimolar per second. Right. So the answer really is just as simple as subtracting those two, and you get a flux of 1 millimolar per second. All right, so that's question number 8. Question number 9 here. What are the key regulatory steps of glycolysis? All right, there are 3 of them. There's hexokinase, HK, there's phosphofructokinase, and there's pyruvate kinase. All right, those are the 3 key regulatory steps of glycolysis. Now, all right, some of the evidence that these are the key regulatory steps comes from the fact that these have strongly negative delta G values. So question number 10 is asking you, why do the key steps of glycolysis have these strong negative delta G values? I.e., how is the fact that they have a strong negative delta G evidence that they are a likely control point? All right. Well, why is this? Well, because in this question I'm talking about actual delta G. I didn't say delta G naught or anything like that. All right, so let me write this out. Erase some stuff here. All right, so our equation for delta G is delta G naught plus RT times the natural log of Q, where it's just concentration of products over concentration of reactants. Now, a likely control point is going to be one in which the rate of the enzyme reaction is very slow. So it's a rate limiting step of the pathway. Now, our rate limiting steps of the pathway, if our reaction is slow, that means there's going to be a lot of reactants for this pathway and a small number of products. All right, so basically the denominator here is going to be bigger than the numerator. All right, and as a result here, this fraction here should be less than 1. All right, now the natural log of anything less than 1 is going to mean that this whole part of the equation here is a negative number. So it's going to be less than 0. So if we have basically a negative portion here, that's going to tend to reduce delta G and make delta G more negative. All right, so any of our steps that have a strongly negative delta G, that's pretty good evidence that the reactants basically are building up in the reaction. And as a result, basically, that is evidence that this is a slow step of the pathway and a likely control point. All right. Moving on to question number 11. Sorry for all the background noise if you can hear my kids fussing in the background. All right, question number 11. Explain how a substrate cycle can be beneficial to an organism. All right, a substrate cycle can be beneficial to an organism in 2 ways. All right, one is substrate cycles can basically burn energy and generate heat. All right, so that's one, and we haven't talked about this a lot yet. We'll cover this in a later chapter in more detail. But basically, by cycling around a substrate cycle, we often burn ATP in the process, and as a result, heat is produced. All right. Now, the second way a substrate cycle can be beneficial is by enhancing the ability to turn on or turn off a pathway. So it basically enhances the regulatory ability of a pathway.
What, Dad? You're writing on your computer with the pencil?
I am. Be quiet. All right. So it enhances regulation. All right. Now, if you imagine, for instance, we have two reactions. We have a forward reaction and a reverse reaction. All right. Now, I'm just going to give these some arbitrary rates. I'm going to say that the forward one has a rate of 10 and the reverse one has a rate of 5. Well, let's say that I can change the forward reaction by half. All right, so it can basically go from 10 to 5, right? And let's also say I can change the reverse reaction by half. All right, it can basically, or maybe I can amplify this one from 5, let's say, to 10. Well, now basically by having both of these combined with one another, the flux now, all right, so normally when our forward reaction is 10 and our reverse reaction is 5, our J value is going to be 2. All right. Now, if we reduce the rate of the forward one by 5, or by half, and amplify the rate of the reverse one by 10, our J value now is -5. All right. So we've basically caused a total change in the flux of about 7. All right. Whereas in either case, the rates of the forward and reverse processes here only changed by 5. So we're basically enhancing our ability to regulate metabolic pathways by including substrate cycles. Now, question number 12. All right, this one's a little bit hard. Hopefully, you guys were looking at the other metabolism of other sugars section of the chapter in order to find some help with this. All right, is what is the net reaction for glycerol getting metabolized into pyruvate? All right, so we're going to go down to the spot of the chapter where we have glycerol. So here's our glycerol right here. All right, so in order for glycerol to get put into glycolysis, we have to go from glycerol to glyceraldehyde 3-phosphate. And it doesn't matter which pathway we go down. Right, we can go this way or that way. All right, the net reaction basically is our glycerol is getting added to NAD plus and then to ATP, and the product is ending up being glyceraldehyde 3-phosphate and NADH and ADP. All right, so we're now into glycolysis here with glyceraldehyde 3-phosphate. Well, what happens to glyceraldehyde 3-phosphate? So this is kind of process 1 here. Process 2 is our glyceraldehyde 3-phosphate is going to react with another NAD plus with the glyceraldehyde 3-phosphate dehydrogenase. It's also going to react with a phosphate. Right? And there's going to be an ADP involved. All right. The phosphate comes in with glyceraldehyde 3-phosphate dehydrogenase. The ADP comes in with pyruvate kinase. And all of our other steps basically we don't have to add any net reactants into those other steps. All right. So then we end up making pyruvate. NAD gets converted into NADH, and the phosphate and ADP get converted into ATP. All right. So now at this point, we can basically add these two reactions together. All right. So we're going to end up with glycerol. All right. Our glyceraldehyde 3-phosphates are going to cancel out since they're on opposite sides of the reaction here. So we're going to have our glycerol plus, right. Hang on, I might be missing something. Give me a second to think here. Yes. All right. So we actually add in a phosphate, and actually there are two ADPs. Sorry, my bad. Two ADPs here. And we end up with two ATPs. All right. the reason why. So we have one of these ADP is getting used and turned into ATP with phosphoglycerate kinase, and the other one with pyruvate kinase. My bad. So I forgot the 2's on there. All right, so net reaction now is our glycerol plus 2 NADs, right? And in the reactants here, we have an ATP, and the products we have 2 ATPs. So one of those is going to cancel out, right? In each case, so we're going to lose this ATP in the reaction. Also, our ADPs, we have 1 of the products and 2 in the reactants here. So we're going to cancel those 2's, and this one's going to go away. All right. And so now we have glycerol plus 2 NADs plus a phosphate plus an ADP reacting to give us 2 NADHs, our pyruvate, and 1 ATP. All right, so that is the net reaction now for glycerol getting turned into pyruvate. Glycerol plus 2 NADs plus a phosphate plus an ADP, giving us pyruvate, 2 NADHs, and an ATP. All right, so glycerol basically can be used as a food source to produce ATP, particularly by bacteria. We can also use it as we're metabolizing fats, for instance. Now, question 13, the last question on the problem set. How does the conversion of galactose into glucose rely on NAD+? Right, and the answer here is the UDP galactose epimerase, or glucose epimerase enzyme, is going to carry out this reaction. Right? All right. Now, all right, with our glucose, right here, how do we actually end up converting galactose, all right, which is our C4 epimer? I should draw that. And sorry, this should be UDP. Right, so galactose is the C4 epimer of glucose. Right, how do we convert this into glucose? All right, well, the answer is we end up temporarily oxidizing this carbon. Right, so this carbon right here has a hydrogen on it as well. Right, so this enzyme is going to deprotonate this, have this collapse back down and make a ketone, and that is going to kick off here a hydride. So in order for this enzyme to work, we have to have a hydride acceptor. And that hydride acceptor that we use is NAD+. All right, and so as an intermediate here, I'm just going to draw the ring structure. All right, at that position, basically, I guess I'll draw all the others. OHs. Oops, sorry, should be up. As an intermediate, we end up with a ketone at that position, at carbon number 4. All right, at this point, since we have a ketone there, we can now make either alcohol. We can have the alcohol going up or the alcohol going down by re-adding the hydride to a specific side of the ring. All right, so that NADH now that's in the active site, so the NAD just picked up a hydride, so it's now NADH. All right, that H- can come over here, attack from the other side, all right, protonating the alcohol, and the end result now is that we have turned galactose now into glucose. All right, by basically using our NAD, so the NAD's role here is to remove a hydride, turning the alcohol into a ketone, and then to add the hydride back in on the other side of the ketone, forming the other isomer of the other epimer, sorry, of that sugar. All right, and that is it for problem set 17.